Okay. The Committee on Science, Space, and Technology will come to order. Without objection, the chair is authorized to declare recesses of the committee at any time. Welcome to today's hearing entitled Unlocking the Secrets of the Universe, Gravitational Waves. I'll recognize myself for 5 minutes for an opening statement and then the ranking member. Last September, American scientists in Louisiana and Washington State detected a signal from an event so powerful that it sent a detectable ripple 1.3 billion light years ago through time and space to Earth. Albert Einstein was right. Gravitational waves do exist. A century ago, Einstein developed his theory of general relativity. He then predicted that intense energy events like the collision of black holes could cause such disruption to the universe that they would emit waves that distort time and space, much like the ripples on a pond caused by a thrown rock. After decades of effort, scientists have now observed Einstein's theory in practice. They witnessed the effect of two black holes colliding, which released 50 times the energy of all the stars in the universe put together, that emitted a gravitational wave across the universe that was, for the first time, detected on Earth. The discovery was the work of hundreds of scientists, decades of ingenuity and innovation, and the commitment of the United States through the National Science Foundation. 40 years ago, a group of scientists began to design an experimental system to detect gravitational waves on Earth. Then they submitted a proposal for funding to the National Science Foundation. In 1990, the National Science Board approved funding for the project. Since that time, NSF has supported development of the Laser Interferometer Gravitational Wave Observatory, or LIGO. This included construction and upgrades, operations, and research awards to scientists who study LIGO data. Today, we will learn more about the value to America of that investment. We will also hear about the monumental success that has resulted from advances in physics, astronomy, engineering, and computer science. The NSF's support for the LIGO project is a great example of what we can achieve when we pursue breakthrough science that is in the national interest. We have the privilege today of hearing from a panel of witnesses who helped make the discovery. They are leaders of the 1,000 scientists and 80 scientific institutions that make up the global LIGO scientific collaboration. We look forward to hearing more about the discovery, what it means for American science and innovation, and what new research and applications may be generated by this breakthrough. With this discovery, we embark on a new and exciting time for American physics and astronomy, and we move closer to a better understanding of the universe. This is a quote by Dr. Kip Thorne, a renowned American physicist and one of the founders of LIGO. With this discovery, we humans are embarking on a marvelous new quest, the quest to explore the warped side of the universe, objects and phenomena that are made from warped space-time. Colliding black holes and gravitational waves are our first beautiful examples, end quote. Congratulations to the scientists on their great discovery. That concludes my opening statement, and the gentlewoman from Texas, Eddie Bernice Johnson, is recognized for hers.
Thank you very much, Mr. Chairman. I'm delighted that you're having this hearing today. It is gratifying to be hearing about a very exciting scientific breakthrough. I want to congratulate each of the panelists and welcome you for your role in anything that you participated when it comes to LIGO. Thank you for being here this morning to talk about what this achievement means for science and for our nation, and about the long-term commitment to high-risk basic science that made it possible. The story of Laser Interferometer Gravitational Wave Observatory is a story about the talent, creativity, perseverance of U.S. scientists and engineers. It is a story about the 65-year commitment of the National Science Foundation to high-risk basic research. I truly believe that a Nobel Prize will be coming. And it is a story about what we stand to lose as a nation if we fail to maintain faith in our scientists and in the scientific process exemplified by the National Science Foundation, that is the envy of nations around the world. When LIGO was first proposed by a small group of physicists from MIT and Caltech, many scientists responded, "You're crazy. It is not possible to build a gravitational wave detector." Many of the scientists of the National Science Foundation and the National Science Board also quietly wondered if it was possible. But the project leaders presented a compelling plan, and the foundation, then under the administration of George H.W. Bush, decided to take the gamble, because that is what the National Foundation, Science Foundation does. It supports high-risk, but potentially high-reward basic research that nobody else will do. Today, we celebrate the scientific and technological achievement that LIGO represents. However, the path to this point was not smooth. When the National Science Foundation first proposed to build LIGO, debates raged in the scientific community and in Congress. Many scientists were concerned about protecting funding for competing physics and astronomy projects that were also important. They were also concerned about squeezing resources for research grants. Those concerns were understandable and eventually led to the creation of a separate facilities construction account at the foundation. Members of Congress, including members of this committee, were also skeptical. This was a very expensive project, and some scientists doubted that it was technologically feasible. Members also wondered, what exactly are gravitational waves, and why should we care? Throughout these debates, despite the elimination of funding by Congress in the first year of that LIGO was proposed, and that the attempt to do so again in the second year, the National Science Foundation kept faith in the scientists and in its own mission. Notwithstanding some of the debates we have had here in recent weeks, the primary purpose of the National Science Foundation is not to strengthen national security or improve public health, or even to grow our economy. To be sure, those are all critically important outcomes of the National Science Foundation investments in basic research across all fields of science and engineering. And some NSF-funded research has intended applications even at the proposal stage. However, the essential core purpose of the National Science Foundation is to promote the progress of science, whether or not there is a foreseeable or intended application, and to train the next generation of U.S. scientists and engineers. And it is clear that the Foundation's bold investments in LIGO, driven by the core purpose, have led to a major scientific breakthrough. Today's hearing served as a reminder not just how talented U.S. scientists and engineers are, but of why we must work hard to maintain our status as the best country in the world to do science by continuing to fund NSF and encourage high-risk taking. This is a lesson that we should apply to the entire agency, not just to certain fields of our choosing. 25 years ago, many members of Congress did not want to fund research for gravitational waves. After all, how was that in the national interest? But enough members did dare to imagine, and here we are today. Again, I want to thank you and congratulate the witnesses, and now we'll yield back the remainder of my time.
Thank you, Ms. Johnson. I might point out that 25 years ago in 1994, we had a Republican-controlled Congress who took the lead in funding LIGO, and I know it was a bipartisan effort, but it's nice to see that reach over the span of 25 years. Our first...
Could I yield to Mr. Foster about a minute?
Sure. We'll recognize the gentleman from Illinois, Mr. Foster, for 1 minute.
Well, thank you, Mr. Chairman, and thank you to the witnesses for coming here today to talk about this very exciting discovery. As the only PhD scientist in Congress, I'm probably more excited about this than most others who've come to hear this today. A century after Einstein theorized the existence of gravitational waves, 50 years after Ray Weiss began thinking of an interferometric gravitational wave detector as part of a class exercise at MIT. 40 years after the spin down of orbiting neutron stars started giving the first hints that gravitational waves were being emitted from astrophysical sources. And 25 years after the National Science Foundation began courageous and sustained funding for an international collaboration of hundreds of scientists to begin constructing this large and technically risky project, physicists have spectacularly confirmed Einstein's theory. This is a discovery that will live on in the science textbooks forever. And with this discovery, we have opened a new window onto the universe, and we have verified that our new telescope is working, and now the fun begins. Thank you, and I yield back.
Thank you. Thank you, Mr. Foster. I keep telling Dr. Foster that my going off to college thinking I was going to be a physics major counts almost as much as his PhD, but not quite. Our first witness today is Dr. Fleming Krim, Assistant Director, Directorate of Mathematical and Physical Sciences at the National Science Foundation. Dr. Krim joined NSF in 2013. Prior to his time at NSF, he was the John E. Willard and Hillsdale Professor in the Department of Chemistry at the University of Wisconsin-Madison, where his research group used lasers to understand chemical reaction dynamics that occur in gases and liquids. Dr. Krim has lectured around the world and published more than 150 papers. He received his bachelor's degree from Southwestern University and his PhD from Cornell University. Our second witness today is Dr. David Reitze, Executive Director of the Laser Interferometer Gravitational Wave Observatory at the California Institute of Technology. Dr. Reitze's extensive work in the area of experimental gravitation wave detection dates back to the mid-1990s. He has authored or co-authored over 250 peer-reviewed publications. Dr. Reitze is currently a fellow of the American Physical Society and the Optical Society and has served on numerous scientific advisory and program committees within the physics and optics communities. Dr. Reitze received his PhD in physics from the University of Texas at Austin. Our third witness today is Dr. Gabriela Gonzalez, Professor of Physics and Astronomy at Louisiana State University, where her research involves the detection of gravitational waves with interferometric detectors. Dr. Gonzalez was a founding member of the LIGO Scientific Collaboration and has participated in the commissioning of the LIGO detector at the Livingston Observatory. Dr. Gonzalez received her master's degree from the University of Cordoba in Argentina and her PhD from Syracuse University. Our final witness is Dr. David Shoemaker, Director of the LIGO Laboratory at the Massachusetts Institute of Technology, where his research focuses on instrumentation to enable the observation of gravitational radiation by precision measurement techniques. Dr. Shoemaker's work in the field of gravitational wave detection began in 1980. He spent several years at Max Planck in Garching, Germany, and the CNRS in Paris, France, where he helped to develop specific technologies for gravitational wave detection. Dr. Shoemaker has served on numerous scientific advisory and program committees for the NSF, NASA, and for the European Gravitational Wave Observatory. He received his master's degree in physics from MIT and his PhD in physics from the University of Paris. We welcome you all. We really appreciate your efforts in being here. You all are the experts. You led the way in one of the greatest scientific discoveries that we will ever hear about. What really caught my attention was the energy release being far beyond the energy of all the stars in the universe. That tends to rivet one's not only attention but imagination. So we appreciate you all being here, appreciate your expertise, and Dr. Krim, will begin with you.
Thank you, Mr. Chairman. Before I begin my remarks, I would like to show a short video clip, just over 1 minute, on LIGO and its detection of gravitational waves.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
The gravitational wave stretches space in one direction and compresses space in the other direction.
Nobody really believed that you could ever detect them because the size of the effect is so small.
I came to the conclusion that, yeah, if you made this long enough,
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
That's what scientific discovery is really all about. You don't choose the simple things to do.
We have done something which is brand new.
The field has busted wide open.
It's monumental. It's like Galileo using the telescope for the first time.
I looked at it and I thought, my God, this looks like it's it.
Thank you. We won't count that against your 5 minutes.
Thank you very much. Mr. Chairman, Ranking Member Johnson, and members of the committee, I appreciate your interest in the historic observation of gravitational waves by the Interferometer Gravitational Wave Observatory. My colleagues will describe the exciting science, but I will spend a few minutes describing the role of the National Science Foundation and the rewards of fundamental research. Although Albert Einstein predicted gravitational waves in 1916, their direct observation was a daunting, seemingly impossible task. Nonetheless, the possibility of opening a new window on the universe was so tantalizing that NSF began funding research on prototype laser interferometers in the 1970s. In the 1980s, the NSF committed almost $300 million to a group led by Kip Thorne and Ron Driver of Caltech and Rainer Weiss of MIT to transform these prototypes into a full-blown gravitational wave observatory. This effort, driven by brilliance, vision, enthusiasm, experimental prowess, and deep theoretical insights, persuaded the NSF, the National Science Board, and Congress to take a risk. Even though NSF had never funded anything on such a scale, the potential for transformative science was worth it. LIGO was the first of our major research equipment projects, now known as MREFC projects. It illustrated the importance of distinct funding for instruments of this scale and prompted fruitful discussions with Congress. NSF embraced a new role in funding large, high-risk, high-reward research platforms, serving the nation by betting boldly on the future. The National Science Board approved construction of LIGO in 1990, and following congressional approval, work began in 1994. LIGO started operations in 2002, allowing researchers to gather data and develop innovative technologies. One of the primary motivators for this arduous research was the question of whether it was possible to build an instrument of the requisite sensitivity. Indeed, the answer turned out to be yes. Thus, in 2008, NSF and Congress understood the compelling case and approved the $200 million of funding for constructing the next generation, Advanced LIGO, the instrument that detected a gravitational wave last fall. That gravitational wave arose in the collision and merger of two black holes approximately 1.3 billion years ago. The wave propagated to the detectors in Livingston, Louisiana and Hanford, Washington, produced the chirp that opened a new window on the universe. This discovery is a beginning, not an end. It marks the birth of gravitational wave astronomy, a new tool for understanding the cosmos. The really good news is that Advanced LIGO is designed to be 3 times still more sensitive and should begin observations with even greater reach this summer. The United States has led this international collaboration. However, continued close cooperation with our international partners is key to taking the science to the next level. New observational capabilities that our partners in Europe, Japan, and India are either building or planning promise an exciting future. LIGO is a national and international collaboration in which cooperation drives the science and leverages precious resources. The LIGO Scientific Collaboration is a group of more than 1,000 scientists at universities around the United States and in 16 countries. I'm pleased to add, Mr. Chairman and Ranking Member Johnson, that for 30 members of that collaboration come from Texas. Mr. Chairman, this historic measurement illustrates the importance of NSF and exemplifies its role in advancing discovery. The majesty of exploring our universe motivates this ambitious experiment. But as with all fundamental science, LIGO offers other important benefits. The science will advance education, inspiring students and developing the workforce our society requires. It has and will continue to spawn collaborations in engineering, computer science, and other fields to make the nation more competitive. The fruits of NSF-sponsored research drive our economy, enhance our security, and ensure our global leadership. Basic research is uncertain and risky, but it is also revolutionary. LIGO is a striking example, but not the only one. Fundamental science has transformed our world and will continue to change it in ways we have not yet imagined. All the contributors to LIGO, scientists, the National Science Foundation, the National Science Board, and members of Congress deserve to take enormous pride in our collective accomplishment. These comments conclude my testimony. I'll be pleased to answer questions.
Thank you, Dr. Krim and Dr. Reitze.
Chairman Smith, Ranking Member Johnson, members of the committee, thank you for holding this very important hearing. I'm delighted and honored to be testifying before you today. My name is Dr. David Reitze. I'm the Executive Director of LIGO. I'm based at the California Institute of Technology. On February 11th, my colleagues and I announced to the world the first detection of gravitational waves from two colliding black holes. This is truly a stunning discovery. It comes 100 years after Einstein first published his general theory, which predicted gravitational waves, and it was made possible only after a 40-year dedicated effort of experiment and theory funded by the National Science Foundation with your support, with congressional support. This discovery is, in and of itself, an incredible scientific and engineering feat, and it proves that Einstein was right once again. However, the detection is really much, much more than that. Up until this point, humanity had never observed two colliding black holes merging to form one. All right. This is a stunning discovery. It's what my colleague Kip Thorne calls a storm in space-time. For the first time, we're probing the universe in a completely new way. Indeed, before this discovery, we hadn't even known that black holes existed in pairs. LIGO is a new kind of astronomical receiver similar to a radio telescope and can directly hear vibrations in space-time. The gravitational window opened by LIGO dramatically differs from all other windows. LIGO should be able to detect things that no other type of astronomical telescope will detect us. Einstein tells us that space-time is warped, that gravity is geometric, and that black holes exist. It also predicts the existence of gravitational wave. As you pointed out, Chairman Smith, there are ripples in the fabric of space-time. The effect of gravitational waves is mind-bogglingly tiny. So it takes massive objects, 30 stellar mass black holes, colliding with each other to produce detectable waves, and the changes that we measure to detect them are 1/1 billionth of 1/1 billionth of a meter. Incredibly tiny. That's a tiny fraction of a proton's diameter. First slide, please, Jose. To detect gravitational waves, LIGO uses two interferometers. You see the one from Livingston, Louisiana, each having 4-kilometer arms. And the signal that we record is actually in the audio band. In other words, we can hear the signal when we play it through a speaker. And Jose, could you play the first? That is the sound of two black holes colliding. Play it again. Play the next slide, please. This makes it a little bit easier to hear. We've just frequency shifted it. Thank you. Like many scientific discoveries, LIGO had very humble beginnings. Experiments were carried out in the 60s and 70s by Rainer Weiss of MIT and groups at the University of Glasgow in Scotland, and by Ron Drever and the Max Planck Institute in Germany, along with theoretical efforts in gravitational wave physics by Kip Thorne of Caltech, as well as others. When LIGO was first proposed as a large-scale project in the mid-1980s, some deemed the project too risky and too expensive. NSF, however, recognized both the huge scientific potential and the cutting-edge technology that could result from designing and building LIGO. I believe this discovery is truly a scientific triumph, but I want to set aside that for a moment and focus on some broader impacts. LIGO in the U.S. leads the world in this new form of astronomy. Large-scale interferometers are currently under construction in Italy and Japan, and India just last week announced that it will partner with the LIGO laboratory to construct a third identical LIGO interferometer in India. The world is following the U.S. into this new scientific frontier. In addition, to make LIGO work, we had to develop the world's most stable lasers, the world's best mirrors and optics, some of the world's largest vacuum systems, as well as push the frontiers of quantum measurement science and high-performance computing. We use a lot of technology, and all the technology we use, we advance. In addition, LIGO is a big data generator. We produce almost 1 petabyte, that's 1 million gigabytes of data per year. LIGO scientists develop and employ sophisticated computer algorithms to sift through the data searching for these gravitational waves, and we use numerical modeling to model the signals that we expect to see, and that requires high-performance computers, supercomputers supplied by NSF's Succeed and Blue Waters program. All of this said, I believe that the largest impact from LIGO in the past and in the future will continue to be the scientific workforce, the education of scientists and engineers that we've done over the past 40 years and that we'll do going forward. Many scientists, when they come to LIGO, they fall in love with it and they choose to stay. However, others go on to distinguished careers in both high-tech industry and in national laboratories. And in addition, LIGO invites about 20,000 students every year to come and visit our observatory education and outreach program. I'll close with the following statement. LIGO is a testament to the vision and tenacity of scientists like Rainer Weiss, Kip Thorne, Ron Drever, and others who began these research programs. But it's also a testament to the National Science Foundation, whose bold vision and steadfast support and stewardship enabled this discovery. It's with great appreciation that I also thank the U.S. Congress for recognizing the importance of this research and supporting it. Thank you.
And thank you, Dr. Reitze and Dr. Gonzalez.
Chairman Smith, Mr. Bayer, and members of this committee.
Is your mic totally on or close enough? There we go. Thank you.
It is an honor to testify here on behalf of my collaborators. We thank you for your interest and support of gravitational wave science. I'm Dr. Gabriela Gonzalez, a professor of physics and astronomy at Louisiana State University and the current elected spokesperson of the LIGO Scientific Collaboration, or LSC. Ours is an international collaboration that succeeded recently in detecting gravitational waves from black holes and will keep opening a new window to the universe. Can I have the first slide, please? As shown in the slide, the LSC, which includes the LIGO laboratory, has more than 1,000 members in 15 countries, with more than half of those in the US. The collaboration was formed almost 20 years ago and is the entity that carries out the LIGO scientific research program. The LIGO laboratory and the US scientists have played a key and very important role in the LSC scientific and leadership activities. Also, LIGO has fostered a very effective relationship with other collaborations, with the European Virgo collaboration and with the Japanese KAGRA collaboration. The LIGO India project, just approved by the Indian government, is part of the LSC effort. We really lead the world. As shown in the next slide, can I have the next slide, please? The LSC has a great diversity of colleges and universities in 22 different US states. There are top-tier private universities, large state universities, undergraduate and liberal art colleges, as well as institutions with many underrepresented groups in science. The collaboration effort is very broad, includes research in many different areas. And this investigation, all these activities are geographically very distributed, but the benefits of our research, like the recent detection, are common to all. That is one of the strengths of collaborative work. We do not receive funding as a collaboration. Each LSC group seeks funding from agencies for their research based on their own individual merits. In the US, the NSF funds the LIGO laboratory with a cooperative agreement, but also funds the basic research in the many other US groups through the very competitive research award system, and that guarantees the quality of the funded activities. Can I have the next slide, please? In this chart and in these pictures, you can see that more than half the LSC members are graduate students, postdoctoral scholars, or undergraduate students. These are young, busy, and happy investigators in training in a very interdisciplinary and international scientific environment. Undergraduates contribute to the LSC research program, not only in the LSC groups, but also in research experience for undergraduate programs in the US, funded by the National Science Foundation. The training in LIGO of all these young scientists, it's done at the forefront of science and technology. It's multidisciplinary. It involves precision measurement technology, big data analysis, a constant need for diagnosis and problem solving, as well as basic physics and astrophysics. There are many career options available to LSE trainees in academia, national laboratories, and high school science education, as well as cutting-edge industry. We compiled an incomplete list of companies employing LSE graduates, and they are now working in the human genomics industry, the US healthcare industry, biomedical information, oil industry, Microsoft, Google, Boeing, SpaceX, Northrop Grumman, Synaptics, Celestron, Luminate, Cytec Engineered Materials, GE Global Research, Geneva Trading, Seagate. We are training the workforce in the US. Many members of the collaboration dedicate a significant fraction of their time to K-12 education and outreach. And that pays off. The public's curiosity about our discovery has been intense. Only last Saturday, almost 1,300 people, some driving for hours to get there, visited the LIGO Science Education Center at the LIGO Livingston Observatory in Louisiana. This Science Education Center is also funded by NSF. And they went there to see where the science is done and meet some of the scientists who do it. The national as well as the local coverage of our detection showed the broad spectrum of scientists working on this field everywhere. There are many local heroes to celebrate. In conclusion, the LSE will continue working hard on its mission to understand the universe better through the newly opened gravitational wave window. We are very proud about the result of our work, not just being amazing astrophysical results, but also pushing the technology and contributing to the progress of society. We thank NSF and the US Congress for the support of our activities.
Thank you, Dr. Gonzalez. Dr. Shoemaker.
Chairman Smith. Right. Chairman Smith, Ranking Member Johnson, and members of the committee. Thank you for holding this hearing and inviting me to participate today. I too would like to thank the committee for its interest in gravitational waves and LIGO, and I hope our testimony helps the committee in its work. I'm Dr. David Shoemaker. I'm with MIT in Cambridge, Massachusetts. My role was to have the pleasure and honor to lead the Advanced LIGO project. Let's take a look at the first slide, please. This was a major project, MREFC, and it came in on time and on budget. If we look at the next slide, please. To round out our testimony, I want to paint a broad picture of our field and its future. Let's look at the next slide, please. What you see here are various images of people at work in the process of putting Advanced LIGO together. So our first goal is accomplished, as you heard. We made a detection, a remarkable thing, but it's just the start of a new astronomy. There are more kinds of sources that LIGO can expect to see. Let's look at the next slide. That's great, thank you. One of the ones that I want to talk about are neutron stars. These are stars which have collapsed from their original size, not all the way back down to a black hole, but to material so dense that a single teaspoon would weigh 10 million tons, if you can imagine such a thing. They tend to be magnetized and spinning, and they've got some strange things going on in their interior that we don't understand. They also can form binaries like the black holes that we saw, and if we can observe them both with our gravitational wave detector as well as with satellites in space that NASA puts up to look at X-rays and radio telescopes on the ground that the NSF supplies for observatory, we can put together all this information into a complete package and know more than we could have ever known without gravitational waves or without this combination, this synergy of information. So it's a wonderful new way to reuse tools that have been used for astronomy in the past and also to learn new things about space and nature that we couldn't have learned otherwise. We have other ideas of things we'll see. Supernovas are rare, but they would be wonderful to see. Modelers still don't know how to make them explode, and we might be able to answer that question. They're collapsing stars, they're cosmic strings, they're defects in space-time. There will certainly be surprises. There are a lot of things that every time we open up a new window to the universe, we see new things, and we're surprised every time. I think this is going to be another one of those surprises. Just as we need radio telescopes and optical instruments in the electromagnetic spectrum to see the full range of possibilities, we'll also want different kinds of gravitational wave detectors in the future. already underway is using isolated neutron stars, these funny magnetized spinning stars, looking at their radio signals from neutron stars throughout the universe, bringing them back down to the Earth and forming a complete picture of what we see and resolving that there are ripples in space-time between the Earth and these neutron stars that may soon yield a result that gives us our first ideas of what it's like for galaxies to be spiraling together. But really, the ultimate way of doing that kind of thing sometime in the future would be to have a space-based antenna. Instead of having 2.5-mile-long arms, in space you could make 2.5-million-mile-long arms. Our sensitivity grows with the length of those arms. You could do phenomenal science that way. And at some point, that will be something I think the scientific community will feel we must do. Coming back to Earth, let me say a little bit about LIGO. Next slide, please. Sorry. The first events were only seen with 1/3 of the full sensitivity that we believe this instrument currently can do. Right now, we're tuning it, we're increasing its sensitivity, and we think that we'll be able to run again sometime in the fall, making more observations. We're hoping that when we next run, we'll be running with the French-Italian detector, Virgo, which should be coming on just at about that time. And with 3 detectors, you can do a great deal more science. You can see where the source is in the sky, and you can get an idea of what the polarization nature is. It will really add to what we can learn, and it leverages our investment to have, as people were saying, these other projects that are coming along behind us, but will add to supplement the science we can do and complement the science we get from our own detectors. We are the leaders. But with these other observatories, we will have a worldwide global cooperation that will bring us all forward in science. Once tuned, advanced LIGO can go even further with modest technology changes. We're learning how to squeeze light, how to get more uncertainty out of our measurement and improve our resolution by using squeezed states of light. We also are looking into making better optics, in particular ones that have new and better coatings on them that can reduce noise in certain areas. And it could be, at some point in the future, if this field comes alive the way we think it will, that we'll need a new observatory. It's not there yet, but that'll happen. So the window to this new world of gravitational waves has just been cracked open. As we open it wider, and more people look out on the landscape, we'll be rewarded with discoveries that will, time and time again, give us all, scientists, students, leaders, and laypersons, a thrill of understanding things much bigger than ourselves. Thank you for your time. Thank you for your interest in our science and your continuing support for the spectrum of innovations in science and technology that we see in the United States. We hope this glimpse of our field has allowed you to share in the sense of accomplishment you have enabled.
Thank you, Dr. Shoemaker. Thank you all. Let me recognize myself for questions, and I'd like to ask quick questions and ask you all to give brief responses if you could, just to get through all these kinds of comments. But first of all, what are the practical consequences of, or practical applications of gravitational waves? Dr. Grimm, any thoughts on that?
Detecting gravitational waves is this fundamentally inspiring scientific problem. And the point that David was just making about a new window on the universe, instead of just looking in the electromagnetic region or just looking at particles from space, we now can look at, we can now look in a completely different way and see new things. But the practical consequences of doing this are really what Gabby was talking about. They have to do with workforce and they have to do with technology. There are miracles of vibration isolation and none of us really believe they're miracles, but they are remarkable efforts at vibration isolation, laser stabilization. All of those are spinning forward into technologies that are extremely important to the country. In addition, the students, and I was very impressed with your list, Gabby, the students that come out of this are not just doing gravitational wave physics.
Right.
They are going on and transforming the semiconductor industry and SpaceX and many, many areas.
Thank you, Dr. Grimm. You gave several examples. Any other examples anyone wants to mention? Dr. Reitze?
So I'll follow up a little bit. I actually believe what Dr. Krim said, that fundamentally LIGO is about opening a new window in the universe. Just to give you an example, after we announced our discovery, the amount of reaction to it worldwide was awe-inspiring. I learned yesterday that I'm not a social media person, but young people are. There were 70 million tweets about this discovery, which is, to me, mind-boggling. I can focus a little bit on the technology to focus on some of the vibration isolation system. We can't talk about it, but we've been approached by companies that manufacture computer chips that do lithography, and the vibration isolation that we do, all right, because we have such good low-frequency vibration isolation, we keep things still for a long time. That's actually something that could be very, very beneficial for companies that make semiconductor chips. There are other examples, too, that I could talk about, but maybe...
Okay. Anyone, Dr. Gonzalez, anything to add? Dr. Shoemaker, then?
I have one thing that I could add to
sure.
that. Timekeeping is really important in a broad range of activities. I think GPS is one of the things that we most frequently use now, take for granted. It requires general relativity to work, but it also requires very precise timekeeping. And some of the innovations that we've made, both in laser stabilization, as well as these mirror coatings that are low loss and low noise, they help us do a better job of timekeeping, and that really makes a lot of the economy turn, being able to get things to place in time.
Dr. Ricey, let me follow up real quickly. And it is this: what can we learn from the LIGO detector? You mentioned this briefly in your opening statement. What can we learn from the LIGO detector that we can't learn from traditional telescopes?
Well, gravitational waves are dark. They're invisible to the electromagnetic spectrum. So everything we know about the universe comes from X-rays or gamma rays or light or infrared radiation. This is a completely new sector. So in some sense, it's the complete complement of astronomy. And the event we saw, black holes, we believe that you can't see them using conventional astronomy. So that's one example. As David mentioned, cosmic strings. There are a whole host of things that you cannot learn from any other type of astronomy that you can only learn from gravitational waves.
I probably only have time for one more question, and let me address it to Dr. Shoemaker, Dr. Gonzalez, and Dr. Grimm as well, and that is, for instance, Dr. Shoemaker, you mentioned coming surprises. Dr. Gonzalez, Dr. Grimm both mentioned the future. So my two-word question is, what's next?
I'll make a guess, and as a bit of a hope as well, that it will be a pair of neutron stars spiraling into each other, which we may actually see also with our ground instruments. That would be very exciting.
Great, thank you. Dr. Gonzalez.
Let me mention that this discovery of black holes was a surprise. We didn't know that these objects were in abundance out there, and we will now know a lot more about those. So this was the first surprise. We expect other surprises.
You might discover something you're not even expecting.
That's
Probably
right.
so. Dr.
Absolutely.
Grimm.
Your last comment is exactly the point. At the budget presentation, the director of the National Science Foundation, Dr. Cordova, said she wanted to tell us what the next discovery was, but she didn't know because we had to discover it. And I think that is a very important point. Now we have a completely new way to look. I mean, to get out of the electromagnetic spectrum and have the complement of gravitational wave astronomy is remarkable.
Great. Thank you all for your responses. The NSF is well represented here today, so I'm glad for them to hear your comments as well. Now recognize the gentleman from Virginia, Mr. Beyer, for his comments.
Thank you, Mr. Chair. I'd like to begin by thanking the chairman and the ranking member for having this hearing. This is great fun. I love this job just for what we get to learn. And I'd like to welcome the students from Oakton High School from Northern Virginia. Welcome. It's great to have you guys here. I feel like I'm in Bern, Switzerland in 1905 or the United States in July 1969. This is just so exciting. And I have some, forgive me, nerd questions for you guys. And I'm not quite sure who to send them to. So we have the strong nuclear force with the gluon, and you have electromagnetic force with the photon, and the gravitational force is supposed to have the graviton. Gravitational waves and graviton, wave, particle. So tell us about the graviton.
The graviton is actually the particle nature of gravity. What we detect with our detectors is the wave nature of gravity. Those are the gravitational waves. So it's a classical version. Each of these gravitational waves that we detected and the ones we'll detect in the
Will you be
future,
able to find something like the photoelectric effect with the gravitons?
Probably not with LIGO detectors, no.
Okay.
We do not do quantum gravity. That is actually a very hot area of research. But we do classical relativity, which is interesting enough.
Okay.
To
How
follow,
about-
just
excuse
to
me,
follow
Dr.
up on
Reitze.
that, we actually calculated how many gravitons we saw, or how many gravitons were released in this experiment, or in this black hole collision. Number's 10 with 80 zeros after it. So there's a huge number of gravitons here. We may discover something. We may discover something interesting about quantum gravity that we didn't know before. That's one of the excitements of this business.
Very cool. Does the gravitational wave go at the speed of light?
Yes, that's what we've learned in this experiment, that we've put a limit on it, that it can only, it can't go slower than 0.992 or 993, the speed of light. We believe it goes at the speed of light.
So we didn't know that these black holes existed or were about to collide until we saw the gravitational wave from them and imputed that backwards.
Yes.
Very cool. So Einstein spent most of his life hating quantum mechanics and trying to reconcile quantum mechanics with general relativity. Reconciling gravitational force with the electromagnetic and the strong force. Does this help?
Actually, it's interesting. Einstein, first of all, he goofed when he calculated the first gravitational wave phenomena. He actually got the term of the radiation wrong. He corrected that and fixed it. But later, he actually believed that the effect, first of all, the effect was so tiny that it would never be discovered, so he never worried about it. And then later, he actually believed that it didn't really exist, and he had to be convinced by one of his postdoctoral associates that it exists. So Einstein himself doubted his own discovery.
But Dr. Krim, will the reconciliation between quantum mechanics and general relativity come about?
Well, we are certainly funding researchers who are working hard on pushing the theory and pushing that understanding. That's a great, outstanding question in physics and in science today. But it's interesting to think, if we think about you mentioned the photoelectric effect, the things that gave us hints about quantum phenomena were people looking for often electromagnetic radiation to behave classically. So as we now have the ability to look at gravitational radiation, just as my colleague said, there may be a surprise lurking in there as we go and with this tool start to poke on that behavior.
You know, the cosmologists try to look as far back in time as possible, and we have those initial thousandths or millionths of a second that we can't see. Does gravitational waves help us to get back to there?
Got turned off. We could say that it's unlikely that LIGO with the ground-based observatories will have a chance to see the primordial gravitational wave background. At least our predictions right now, insofar as we understand it, would put them at a level which is too low to be seen. But it could be that either a space-based antenna could be seen, could see these sorts of effects, or these ground-based antennas, which have been looking from Antarctica to try and understand the polarization of the Big Bang background. I think those experiments will also give a positive result shortly. I hope they will. That would be a very exciting result.
Let me say that one of the questions that people are drawing from, one of the conclusions they're drawing from our observation is how early or how late the black holes formed. That is not well known at this point, and our observations are the ones giving clues about the origin of the small black holes.
Dr. Reitze, one last question. String theory, yes or no?
No. Maybe. Thanks, Ms. Beyer. The gentleman from California, Mr. Rohrabacher, is recognized for his questions.
Thank you very much, Mr. Chairman. I've got a wild question at the end to ask you, but in the meantime, let me just go some business here. We started off this program with a $300 million grant in 1980. Is that correct? That's okay. And how much?
94 was actually when that was made.
Okay, so okay, I thought that you said it was 1980. How much then? Okay, so from 1994 was the first major expenditure of $300 million?
That was when we went to the phase of actually constructing LIGO. But these earlier dates, where we're talking about funding research starting in 1979, had to do with a lot of demonstrations of both technology and science. For example, people built tabletop laser interferometers to start to show that they could reach the kinds of sensitivities. There was a chance to get there. My colleagues here can tell that story in some detail, but this is a pattern that we often follow. We start out funding folks who lay the groundwork, and then the community gets together, again, as my colleague said, and makes a compelling argument based on that early theory and experiment.
Okay. So from those early experiments till now, how much are we talking about that's been spent on the project?
We have spent a total of over $1 billion, $1.1 billion. About $450 million of that went into actually constructing initial and advanced LIGO. The rest has supported operations and maintenance of the observatories,
Right.
as well as individual investigators that were doing that early kind of work and the laboratory work I'm talking about.
And how much we talked about everybody's working together and many different countries have contributed. How much have they contributed to this effort?
David, why don't you comment?
So Japan's got started with a detector in the 90s, and they're building a big one. I think their number, and I'm not, don't quote me on this, but I think it's on the order of 250 million. But they're well behind us. I mean,
Is that the Japanese, you say?
that's the Japanese detector. The Italian Virgo detector, I think the way they do their accounting is a little bit different because they don't cost their people in it. So it's not really an apples to apples comparison, but probably they have spent about $200 million, not including the people that they've put into it.
What's the foreign contributions to our?
Oh, I'm sorry. Maybe I misunderstood the question. Foreign contributions to advanced LIGO. David Shoemaker might be able to answer that question.
Let me speak to that. The NSF did fund us for a program to build the advanced LIGO detectors at $205 million, but then of their own free will, the German Max Planck Society, the STFC in the UK, and also ARC in Australia all made contributions with a total value of some $17 million just because they wanted to be part of the experiment. They would have had access to the data, they would have enjoyed the profits of it, they wanted to be part of this activity.
So would it be fair to say we've spent about half the money that was necessary for the project and to be successful as you are today, and the rest of the world spent half of that?
No, our fractional contribution is much larger than that, but as far as getting to the point of this observation, it is sort of 20 million versus 450 million of construction cost. But David was Dr. Reitzel was making an important point. Other nations are mounting large gravitational wave detection elements, and we were working in concert with those. So if you wanted to add up all of that, the money going into CAGRA, the money that's going into Virgo, that becomes a much bigger number. But as far as the U.S. investment in these instruments, it's about what I said.
Well, I appreciate, I've always supported basically research when we're looking out, because I've been told that if we're looking out to outer space that we actually can determine what's going on in the molecular structures that can have major impacts here. And sometimes it's easier to see it out there than it is to see it through your little microscopes. Telescopes and microscopes are actually very related from what I was first educated when I first came here, so I've tried to be supportive of both efforts. Now let me ask a little, I know this, Mr. Chairman, just one quickly. First of all, we're talking about waves, and I'm a surfer, of course. I want to find out about riding waves. But will this discovery that you were talking about today make time travel any more? I mean, this is one thing I've been hearing about. It will make it any more likely.
Beam him up, Scotty.
We wish. This actually does show distortions of space-time. So we measure it as distortions of distance, but it is distortion of time. We can see time traveling faster and slower, but it cannot make us travel in time.
Well, thank you very much.
Thank you, Mr. Rohrabacher. The gentlewoman from Connecticut, Ms. Esty, is recognized.
Thank you, Mr. Chairman, and to the ranking member. And most of all, thank you to the four of you and these huge, exciting team of international researchers. So there are two topics I wanted to quickly touch on. First was the importance, and you've all mentioned it a little bit, but the importance of robust, long-term funding for basic research. You know, if we're going to break those boundaries, reach beyond what we know, it does take that kind of serious, long-term committed investment, even in the face of, if not failure, not the sort of data you would have wanted. So if a couple of you can comment on that, because we're under constant budget strains, and it's really easy for people to say, you know, I have bridges and roads and schools in my district that need fixing, but I also believe that we will be better, not just as a country, but as a species, if we continue this sort of cutting-edge research. So that's one topic. And the other was to talk a little bit, and Dr. Gonzalez, you particularly touched on this, about the diverse STEM workforce and the need to inspire a new generation, the collaboration that comes up, and what efforts are being taken in this project to make sure we're seeing diversity, because I know, you know, a suburban white boy may be thinking about using those STEM skills differently than a woman of color in the inner city. So hoping that we're really making an effort as part of this collaborative endeavor. Thank you very much.
Let me say one or two things about this question of the sustained support for the research. I'm a professional scientist. I'm not a faculty member, and it's been really invaluable for me and for other colleagues in the LIGO laboratory supported by the National Science Foundation to be able to turn our careers to this and choose to, without striving every 6 months to look for another funding source, to be able to make plans, to be able to make small-scale experiments that take years to give results, to work with industries in a cooperative way through the manufacturing cycle. It's that kind of continuity in intellectual input that allows something of this nature to take place. So that's been a very, very important thing to us. Clearly also when students come to us and say they want to do a project with us and we can tell them, you're going to be able to start and finish on this topic, it's something that really gets people engaged, keeps their mind on the science and away from what's happening next. So it's been very valuable to us. Thank you.
And I have to say that it's not only us as members of this collaboration that are inspired to work on this because of black holes and gravity and Einstein. We inspire people too. And we have made a very big effort. We have a big effort in outreach and diversity. We actually try very hard in the US to increase the diversity, not just of our collaboration, but of the scientific workforce in general. We work with the National Hispanic Society of Physics, with the National Black Society of Physics. We have fellowships that we work out with them. So we do have a very diverse effort, but it's been rewarding with this discovery especially to receive questions and visits from school children, from parents wanting their children to learn about this science. We receive emails all day from many school children asking about gravity and Einstein and how do you do this and where is this done and how can I visit? It's the inspiration that we provide that I think it is, it's going to help the diversity of our workforce.
And to that point, if you have not already, I would hope that you are developing materials, links to websites that you can disseminate to us, we can to our districts and to our colleagues to allow that citizen exploration and inspiration, because we find obviously the ability to use the internet really does bring this home. And I can tell you we had the astronauts here in a live link in this room, and I was able to have a live link with an astronaut from my district, and the inspiration for 3,000 school students who could watch a graduate from their high schools speaking to them while he's spinning upside down was extraordinary. And I would hope this has really captured the nation's imagination, so I'd urge you to develop good materials at a variety of ages, and then we'd love to, I know I would, and I know all of us would love to be able to make that available to the students.
We are working very hard on that. We already have a K-12 material about this discovery, and we also have translations of our website and our papers in different languages, including Spanish.
Terrific. Thank you very much. Really appreciate your hard work, and another 40 years for this project. Thank you.
If I can,
Dr. Krim, yes.
Briefly comment to two of your points. Our Directorate for Education and Human Resources has been collaborating with us in generating the kinds of materials that you're talking about. We began thinking about that prior to the announcement in conversations with the leader of that directorate, Joan Farini Mundi. Your comment about long-term sustained funding, and what David had to say about it is really important. We see ourselves trying to find ways to support these long-term risky bets to really get out on the edge and do something transformative. And I think we all recognize the challenges that with the budgets the way they are, but we see that as a constraint, a boundary condition within which we work, and we try what we can to accomplish what David was talking about, to let these projects have the stability. It's not easy. It's a constant dynamic tension.
Thank you all very much.
Thank you, Ms. Esty. The gentleman from Florida, Mr. Posey, is recognized for his question.
Thank you, Mr. Chairman. Thank you for holding this hearing, and want to thank all the witnesses for their participation on this exciting subject. For Dr. Reitz and Dr. Shoemaker, because the expansion of the universe is accelerating, I'm told that the scientists theorize a mysterious dark force is pulling us apart, and that only 5% of the universe is visible to us. They say dark matter is 27%, and dark energy is 68% of the universe. That's just what I read. Can the gravitational waves help us understand the missing dark matter and the dark energy better?
Yeah. So let me start, and David can comment. It may be possible. First of all, gravitational waves themselves exist. They're ubiquitous, just like dark energy and dark matter, but they're a very, very tiny fraction. I mean, you can sort of add up how much energy density is in from gravitational waves, and it turns out to be very tiny. But it may be that gravitational waves interact with dark matter in a way that we haven't theorized yet or calculated. So it may very well be that somebody will come up with an idea to use LIGO or maybe LISA, the space-based detector, to detect them. So it is, it's one of those things where now that we've detected gravitational waves, people are going to start thinking about how can we use it to understand other more fundamental things. Dark energy is trickier. I once heard somebody say that dark energy overstates our energy or our knowledge of this phenomena by 2 words: dark and energy. We really don't even know what it. Yeah, there's getting better understanding of it, but it's still you can measure it, but to understand it is kind of hard.
Let me add that we're already one step along the way by having seen just how well our discovery, our first discovery, matches general relativity. It is astonishing how well Einstein's theory from 1916 matches what we saw, and that already excludes some possibilities for some things going haywire in our understanding of the universe. So that's already a set of constraints, and we think as we see each new source, we'll probably put new limits. Maybe we'll discover something which is different than we expect, and that would really be a key, or maybe we'll find that our theories are better and better confirmed. But either way, this new window on the universe gives us a possibility to close some opportunities that would otherwise not be there to zero in on what the real answer is.
If it took 100 years to go from Einstein's equations to discovering they're actually correct, just wildly thinking, what do you foresee in the next 100 years? And all of you just comment on that if you don't mind.
So my favorite philosopher is a gentleman named Yogi Berra.
Yeah.
And he said predictions are difficult, especially about the future. You can look back 100 years ago when general relativity was first postulated, when quantum mechanics were first postulated, and it was, at least it would have been impossible for me to project forward where we might be. That's the thing about science that's so great, that you never know where your big breakthrough is going to come from. So for example, everybody probably, or some people have been through MRI, getting diagnostic imaging from MRI. That comes from an obscure phenomena that was investigated in the 40s and 50s by nuclear physicists and condensed matter scientists. So I wish I could answer. If I could, I would probably make a lot of money in the stock market, but I just don't know.
We love wild speculation in this committee. and that's just what Einstein was 100 years ago, actually.
Let me say that I also don't have an imagination big enough to think what this will help in 50, 100 years from now. But I think there are surprises that are a lot closer. We are looking at the dark side of the universe. You talk about dark matter, dark energy. We are looking at the dark side, black holes, of which we know very, very little. These surprises are just around the corner. That's what I imagine the best side of this story is.
I want to emphasize how well chosen your time scale is, in that it can take 20, 50, or 100 years for these discoveries to come out of ideas that start to emerge now, and the consequences can play out over those timescales.
I don't have too much to add. I'm an instrument builder. I love the technologies. I know we'll be doing wonderful things with the technologies that we're developing 5 or 10 years from now. What will happen 100 years from now, I have absolutely no idea, but it will be neat.
And finally, Dr. Krim, I was wondering, as the field of gravitational wave astronomy moves forward, how are the NSF and NASA cooperating on supporting the field?
We have a very effective and close collaboration with NASA. The simple way to describe it is we do ground-based astronomy, they do space-based astronomy, but that means that oftentimes experiments we fund are very complementary to ones they fund. For example, we have a collaboration on their exoplanet program, making ground-based radial velocity measurements to understand the mass of planets around other stars. So we have joint committees where we talk constantly, and the physics and astronomy that unites this effort is common to us both, and we're in really good contact.
Thank you. Thank you, Mr. Chairman.
Thank you, Mr. Posey. The gentleman from Illinois, Mr. Foster, is recognized.
Well, thank you all again. And listen, just in terms of technology, I bet you have some fun facts about your mirror specifications and how that compares to the sort of mirror that you look at every day in the bathroom.
Well, I've actually never done any metrology on my bathroom mirror, and so I can't quote you the specifications for it. The optics, which are hanging freely in space to respond to the passing gravitational wave, are right circular cylinders. They're chunks of beautiful, clear fused silica or glass. They're about 100 pounds each. They're about, they're 34 centimeters, about 1/3 of a meter, about 1.5 feet in diameter. Their surfaces are polished to the radius of curvature that matches our 2.5 mile long arms. So they're actually a very, very, very shallow curve, and figured to within a 10 to the minus 9 of a meter across, or 10 to the minus 10 of a meter across the full surface. This is work done by Zygo et al., and they developed these techniques, I think, for some satellites that are looking down on us at this very moment. But they were able to figure these mirrors to an absolutely superb precision. And then on that, we put down layer after layer of alternating indices of refraction to get mirrors which reflect the light back extremely effectively with very little absorption, but then also a curious additional requirement that the mechanical losses in the coating be low. This is part of the thermal noise. It's like the Brownian motion. Everything is jiggling around because it's at room temperature. Our coatings are the things that jiggle the most in our entire interferometer, and that's there where we have to put the most work in the near future in making our technology advances, and those are tough ones to do.
Yeah, and let me just follow up on that. This is where LIGO is so cool in so many ways for me. This is a material. The problem that David just alluded to is a material science problem. We have to solve fundamental material science problems to be able to discover black holes. So there's just a natural connection across lots of different disciplines.
Yeah, thank you. Wow, that is amazing. So cooling the mirror is not going to get around the coating?
It would work. In fact, the Japanese detector, Kagra, which is in the process of now going together, uses this technique of cooling mirrors. The noise goes down as the square root of the temperature, and so it's a pretty hard row to hoe. You have to bring down the temperature of a lot of big equipment in presence of a very intense laser beam. So it's a big challenge. It's going to be somewhere in our future, but I think we can do a lot on the Earth with the LIGO infrastructure without getting into cooling, and I hope we can hold off on the cooling until we really know that it's the best path to take. It's complicated.
But let me say that, like Dave said, this will take fundamental research on coating technology that it's not in hand yet. advancing our detectors, we can improve the detectors. We have technology already to improve the detectors a bit, but to improve them 10 times better, we have to make them 10 times longer or get technology for these coatings 10 times better.
And what do you think the ultimate capabilities of ground-based versus space-based, and what are the sort of sources that you can hope to see with each? And in particular, what would it take to get to the sensitivity where you could have seen SN 1987A, the supernova that was detected in the detector built for my PhD thesis?
Let me say a little bit about the technical limits on the ground. What we will probably find ourselves limited by is the lowest frequency we can observe, which also corresponds to the biggest system of masses that we can measure. And it's finally the fact that the Earth is not just moving, but also compressing and getting less dense as seismic waves pass that causes our mirrors to move, because the amount of Newtonian attraction of the mirror is changing as a function of time. And that's a wall that's about 1 hertz. And that will limit us to, I don't know, something like 1,000 solar masses as the biggest objects that we can really measure on the Earth. And at that point, it will really be the time to go into space and see what's going on there. The others of you want to respond to the other question?
Yeah, if the supernova 1987A went off today and LIGO was online, we have a good chance of actually seeing it. We would have actually seen it. Or if we didn't see it, it would have said something about the dynamics of the core collapse in that supernova process. So there's a star, Betelgeuse, that's a red giant, and it's probably going to explode sometime in the next 10,000 years. We're hoping it explodes in the next, we're hoping it's already exploded and the signal's on its way.
Do you have any graduate students where that's going to be their PhD thesis topic?
They're lining up in 2028. So.
But let me say that the sensitivity to supernova is on the high frequency end as opposed to the low frequency end. And in there, the coolest technologies that we will be applying is quantum manipulation of the light that will improve our sensitivity to supernova.
I see. And so you have an easy way to explain to this committee what squeezed light is?
Sure.
Okay.
All right. So I'm sorry. These are questions we love. Okay. And if you shut me up if I'm getting too boring, I'll be quick. So electromagnetic waves are not very precisely defined. They have uncertainties in amplitude and in phase. All right. And that comes from the natural quantum nature of light. And the way that you distribute those uncertainties, somebody named Heisenberg told us that there was a sort of a little fuzzball. You can think about it, an electromagnetic wave as a vector with a fuzzball at the end. You can actually squeeze the amplitude at the expense of phase or vice versa. So this is something that's existed since the 1980s, and it's actually a technology that hasn't found much of an application until LIGO, and now we're using it. So
thank you. Yield back.
Thank you, Mr. Foster. The gentleman from Kentucky, Mr. Massey, is recognized.
Thank you, Mr. Chairman. My first question is, how frequently do these observable events happen? You know, like when we talk about storms and floods, 50-year storm or a 50-year flood, 100-year flood, this event that you observed, from probability, how soon can we expect to see one of that magnitude or larger again?
Very soon.
Like 5 minutes or 5 decades? Or?
Well, let me tell you, the analysis that we presented was the analysis of 1 month of data taken with the 2 detectors that only had 16 days of effective time when the 2 detectors were working together, and we need the 2 detectors to confirm the signal. And we saw 1 event in 1 month. Of course, you could say you can...
But that either means you got really lucky or your instruments aren't working, or, I mean, it could mean a lot of things. So.
That's right, that's right. So we can only predict from that 1 month of data, we can only say we saw 1 event in 1 month. But we have taken 3 months more of data that we are still analyzing, and everything we see is consistent with what we saw there. And we are going to take more data in the future. And from the theories that we derive, even from this just 1 observation, we have a predicted rate that will mean at least a few a year.
Dr. Shoemaker, you're from the university I graduated from. So I'll give you.
Greetings.
Go ahead.
So one other thing to point out, though, I mentioned that we're at 1/3 of the sensitivity we believe our instruments can achieve with just doing tuning. A really neat thing about gravitational waves, it's an amplitude phenomenon. It falls off as 1/r, not over 1/r squared, the distance from the source to us. If we can increase our sensitivity by a factor of 2, the number of sources within reach goes up as 2 cubed.
So I was going to ask you about that. You said it's going to increase by a factor, or it's going to increase by 3. Did you mean 3x or 3 orders of magnitude?
I mean 3x. That is to
Okay.
say, we'll reach 3
Darn.
times further out.
Okay.
But that means that the effective, sorry, that means the effective rate will go up by 27 if you cube 3. And if we saw one event in 30 days of observing, that says we might get to the point where we're seeing an event every day if this one event we saw is representative of the rate. So I think we can see that there's a lot of progress in the future that we can go to increasing the rate.
And that's just for binary black holes.
Gotcha.
We still haven't seen neutron stars, and we expect to see quite a few of them when we're at this per year when we're at design sensitivity. We talked about supernovas before. They are the ones that are going to be hard to see. We're going to have to get really lucky to see a supernova because they're just not that strong of an emitter.
One of the questions I did want to ask Dr. Gonzalez, you touched on it. Did you remember to leave it on when you came to the hearing? Like, what is the duty cycle? How frequently is this collecting data? And is that, I mean, maybe we've already observed things we don't even know yet, and people just need to sort through that data. Maybe we've already observed simultaneously something that we saw in the electromagnetic spectrum, but we just don't know it yet. Is this thing turned on now?
It is intermittently, but for diagnostic purposes, we are not taking data in coincidence, but we have plans to take more what we call engineering runs, opportunistic engineering runs. We will have another observing run with the 2 LIGO detectors starting in this late summer, early fall, perhaps July. And that's how we will know what the rate of these binary black holes and perhaps other events will be. But let me say, you asked me if I remember to leave it on. It's not me, and that's the strength of having 1,000 people working on this.
Right.
There are 200 people in the LIGO laboratory, and they are the ones who not only keep the detectors on, but they improve them every day.
I have a question I want to make sure I get to ask. What are the sources of noise that you have to contend with? You know, like I imagine our sun is doing something. There may be nuclear tests here on Earth that are causing seismic. Maybe talk radio is interfering. It's a big source of noise, but what are some of the noises you've had to filter out?
Let me say what the basic noise sources are. One of them has to do with the sort of quantum effects that Dave Reitze was talking about. We use lasers, and the lasers emit photons in a statistical way. So there's a fluctuation in the number of photons. So there's a fluctuation in what we use as our measure of where the masses
Can you get smaller photons?
You can. The thing to do is to get more photons.
Okay.
Turn up the laser power. The next thing to do is address these questions of thermal noise that I mentioned earlier on. That everything is jiggling around due to Brownian motion, and the way we address that is to choose materials that have very, very low internal losses and squeeze all of that jiggling into a very narrow frequency band. Lastly, you were talking about seismic motion. We built, and that's one of the really big improvements of advanced LIGO or initial LIGO, a system of seismic isolation, which makes it so that we're effectively independent of the environment around us during normal weather conditions. We still can get knocked out of lock when there's a lot of wind. There was a tornado down in Louisiana just yesterday. So there's
one last quick question before I yield back. When you get this third detector, does that just improve the reliability of your data, or does having a third point on Earth give you an ability to triangulate? Dr. Krim, you were shaking your head. Maybe you could.
All of the above.
All of us are shaking our head, yes. That's
okay.
To both.
But it will give you a bigger picture of what's going on. Can it do that?
It gives you better localization, so you will better pinpoint where the source comes from. But also, if you have 3 detectors, you need 2 to see a signal. If you have 3, you can have one on and the other 2, and then you will still see the signal. With only 2 LIGO detectors, if one is down, we are in the dark.
Gotcha. Thank you. I yield back. I could ask 100 more questions. It's very fascinating. Thank you.
Thank you, Mr. Massey. The gentleman from New York, Mr. Tonko, is recognized.
Thank you, Mr. Chair, and welcome to our panel. What a fascinating panel. Let me congratulate you and all of the people and institutions who have inspired this tremendous moment. It's truly a phenomenal success, and certainly I'm grateful to the people who had the vision and pursued, based upon the seed that they planted, to be determined to come to the success that we've met. So I anxiously look forward to what else is out there, and and can't wait to see what is yet to come. And if this doesn't serve, if this doesn't illustrate the value added of high risk, high reward, basic research, I don't know what does. So hopefully we get the message, we invest deeply and soundly in research and move forward. My question would be to all of you, any of you, what role did partners in industry play in the design and development of the of this novel technology? Certainly, you've got infrastructure that we've seen in your slide presentations. There was a lot of talent you had to draw upon. So can you describe that, please?
Yeah, just a couple of examples. I'll start actually with the first LIGO, initial LIGO, which was built in the late 1990s and 2000s. We partnered closely with a firm called Chicago Bridge and Iron Works that developed our vacuum system. And this vacuum system at the time was the world's, I think, largest, although maybe that's not true from a defense standpoint, and highest vacuum system. And some of the work that they did for us went on to later inform what they did for the National Ignition Facility. We worked closely with a company in Silicon Valley that developed lasers, Lightwave Electronics. They developed the first laser for initial LIGO that was actually used in some other applications, such as newspaper printing. As David mentioned, we worked closely with industry for developing optics and coatings. So that's both in the U.S. and with international partners. We worked a lot with companies in Colorado and Boulder, Colorado, to develop some of the first LIGO mirrors and some of the first coatings, a company called Research Electro-Optics, also advanced thin films. We work a lot with companies like NVIDIA, all right, because we use GPUs in some of our analyses. We're actually not using them right now, but we will be using them, so we're working closely with them. So there are a number of touch points where we've actually partnered closely with industry, and that's just a partial list.
Great. Anyone else that?
That covers a broad spectrum of the things that we used. So.
Was there anything unique in the collaborations that you developed as a LIGO industry? Was there anything in particular that was a different approach?
We developed, actually this was one of the things that I worked on. We had to develop some novel electro-optic technologies for, it's sort of a technical thing about how we keep our interferometer in an operational point. We had to develop something called electro-optic modulator that was actually new and it's patented. It hasn't been licensed. It hasn't been licensed yet. But there are things like that. Some of the work that we did with the silica fibers, I think, with the Glasgow group has been spun off to some other applications too.
And coming back to the mirrors once again, we knew what we needed for mirrors, and so we found the very few bidders, one in Australia and one in France, by the way, who could deal with our basic requirements, but they couldn't actually even measure what needed to be measured. And so we gave them instructions on how to proceed. We worked with them in a collaborative way to develop the technologies that were necessary, and then we brought the optics back to Caltech, where the very finest metrology in the world could be done, and give them feedback about what they needed to make, what kinds of changes they needed to make in their technology. So in that way, we were able to trade things back and forth between the academic side and the commercial sector and work in a collaborative way to get something to push the state of the art forward.
I should mention also that information technology has been used. Many of the algorithms, or some of the algorithms that we developed to search for gravitational waves in the data have found applications in the genomics industry and in some other big data analysis. And that's why some of our graduates actually are sought by these industries.
In particular, the kinds of challenges that we have of looking for small intermittent signals against a complicated noise background are things that the defense industry finds interesting. So a number of people have gone off into that sector and discovered the skills that they developed with us were very useful. We don't hear much back from them, though.
Well, it just shows the emphasis that we have on science and engineering, scientists and engineers to make it all happen. And just quickly, Dr. Reitze, you made mention of the commitment of NSF to fund the development of LIGO as a scientific moonshot.
Yeah.
Can you elaborate upon that,
Yeah,
please?
look, I think Chairman Smith said it, or somebody said it quite well, that when the first time rational scientists hear about LIGO, they think it's crazy because they think, how do you possibly make a device that can measure to the billionth of 1/1 of the diameter of a proton? And you scratch your head. And then you start thinking about it and you realize that, yes, it is possible. So in some sense, this was even bigger than the moonshot in the sense that I think most physicists, and it ran into resistance early on, most physicists didn't believe it could be done. So I think it was due to a few key people, including some key NSF directors early on, Rich Isaacson and Marcel Bardon, that recognized that, yeah, you could do this. It was just amazing.
Just to briefly follow up on that, this is not a discontinuous process. As people scratch their heads, they do calculations, they do experiments, and you persuade people. It's a very critical community competing for precious resources, and people have to make their case forcefully, persuasively, and part of what we try to do at NSF is to balance off all of those really good ideas, and it's a marketplace where people have to really meet a very high standard. And this wasn't some long shot, it was a series of considered bets, and they were risky, but it's paid off beautifully.
Well, thank you, and again, congratulations. And with that, Mr. Chair, I yield back.
Thank you, Mr. Tonko. The gentleman from Georgia, Mr. Loudermilk, is recognized.
Well, thank you, Mr. Chairman, and this is very exciting. It's a very exciting discovery, and I'm very proud that we discovered this here in America. This is the type of thing that we have been known for in the past, and I think it's large in part not just to investment, but to the freedom that we have to investigate and explore. And again, I see it much like the Apollo program, that some of the spin-off technologies that we're going to have, not just from the discovery itself, but the tools and the technology that goes into the discovery, I think is going to benefit future generations. I've also been impressed with the large audience we've had here today, Mr. Chairman. I think this may be one of the largest audiences that we've had, and I really appreciate those students being here. This is the type of thing that I think we're setting the groundwork for future generations. In Georgia, we've had a little bit of a challenge of inspiring our young people to get into science and technology career fields. We have some of the world-class research institutes right there in Atlanta. We're leading the nation in health IT and a lot of innovations and discoveries, but yet our biggest challenge has been filling those jobs with innovators. It just seemed to be a lack of inspiration. But I'm becoming more encouraged by what I see here and something I did yesterday. On my way to the airport, I had the opportunity to stop by one of our high schools and notify 2 students, both high school sophomores, that they had won the app challenge that Congress had put on. Ryan Cabelli of Kennesaw Mountain High School and Alvin Potter of Wheeler High School took technology. They didn't develop the technology, the coding language, but they saw a need with other students, and they took the technology someone else had discovered, and they put it into a practical application called GradeSpark. As they informed me that GPA is everything to these students, and one of the challenges students have is predicting what their GPA is going to be based off of their previous grades. So they have actually developed an app for your phone that students can put their grades in, and they can estimate where their GPA is going to be and what they need to do. And so it's taking the research others have done and put it to a practical application, which I think this next generation will be able to do that same thing. A couple of questions, though. I'm very interested in the technology you're using. I've spent 30 years in the IT sector, but the technology that you use to actually do these discoveries. But first of all, from previous questions, I was very intrigued about what you've discovered about gravity. That, from what I understand, it sounds like there's a lot of properties of gravity that's very similar to light. The speed, that there is actual waves. And I'm drawing a blank here, particles. Are we seeing more and more relationship between the two, the more you discover?
Well, yes, of course, there is a very strong relationship between the sky, what we learn about the sky from the electromagnetic and the gravitational spectrum. We are looking, I think one of the biggest, I wouldn't say surprise because we're expecting it, but one of the biggest events that we expect in the future is seeing a bright source both in the electromagnetic and the gravitational spectrum so that we can learn from the matter and the photons in there. That will be amazing, and it will happen. It will happen soon enough.
But then on the more fundamental question of the similarity of the two different effects, it's true that in both cases it's information that travels at the speed of light, or the speed of gravity as you prefer. In both cases the effect is perpendicular to the direction of propagation of the effect. In both cases, as you make antennas longer, under the conditions of long wavelengths of information, you get bigger and bigger signals. A basic difference, though, is that a photon is a particle that travels in space-time, and we looked at space-time itself as it warped. And so it's a slightly different thing in that sense there.
So as we get to the longer tubes, if I may ask, I'm running out of time, are you already seeing the, I anticipate even at 4 kilometers, you're seeing the gravitational pull on your lasers, a slight, somewhat bend of?
Yeah, we see actually, so we design our instruments so that the light itself, 4 kilometers is not a lot of distance
Right.
for light, and we have to design our instruments so that we take into account the curvature of the
Right.
Earth so we can go flat. But what we do see in our instruments are the tidal effect from the moon goes around the Earth,
Right.
the Earth sort of breathes because of the tidal effects, and that actually shows up on our detectors. It changes the length of our detectors by about 100 microns a day. And we actually have to, we predict it, we can correct for it, and we feed it back so that we don't have to.
Well, that was kind of my other question as far as the calibration factor from seismic activity, and I hadn't even thought about the effect of the gravitational pull on the moon. So these things, it is a lot of technology, as you alluded to, just to go into the research itself, and I applaud you on these great discoveries. Thank you.
Thank you, Mr. Loudermilk. The gentleman from Colorado, Mr. Perlmutter, is recognized.
Thanks, Mr. Chair. Just a couple questions. I find this so fascinating and so over my pay grade, I don't know what to tell you. And you four really are inspiring to me. You talked about being inspirational to your students. You're inspiring to all of us. And thank you for your patience and looking at this and talking about the space-time continuum and warp speed and wormholes and I don't know what else. But just a basic human question for me is like, can you describe the first few hours after the detection? Who found out about it? How quickly did word travel? Was it as fast as the speed of light? Is that how fast the sound was? And just generally, how did the scientific community, individually and as a whole, feel about this discovery? And then I'm just opening up, and you can go one at a time.
Yes, let me tell the story. Actually, it's a very long story. We had been preparing for discovering gravitational waves for a long time. So we have computer programs that produce alerts, and those alerts are alerts in the control rooms, but we didn't have those alerts quite ready yet when these came. So they were producing web pages. Our codes, which are very smart codes produced by very smart people, were producing web pages. And because this event happened in the middle of the night in the US, these web pages were first seen by our collaborators in Europe because it was daytime for them. But that's, again, the strength of having a distributed collaboration. So there was an email flurry saying, what is this? Who is injecting this in our data? So it took us a while to find out that the detectors were all in fine state. This was not a test. This was not a drill. It was a real event. But then we had a very hard work to vet this signal, to convince ourselves that this was a signal. And that took months to vet this signal, to make sure that everything was okay, that all our hundreds of monitoring systems did not register any earthquake, any lightning, anything strange that could have caused this. And then to also analyze this event, to get all the physics and astrophysics out of it. That took months of work by many hundreds of people.
Yeah. We in California are usually the last to know about anything because we're on the farthest time zone. So I got to work, I took my daughter to school and I got to work at 7:30 this morning and I read my emails first, that's my routine. And I saw a number of emails saying, you need to look at this. This is serious. And the more I looked at it, the more I went, wow, this is actually unbelievable. And this thing that Gabby pointed out about injections, one of the things that we do to test ourselves is we inject signals. We can actually wiggle the mirrors to produce the kind of signals that I showed you. And we do it sometimes secretly. So there was after people saw this signal, they said to themselves, oh, this must be a blind injection. And there were only 4 people in the collaboration, and I was one of them that knew that this was not a blind injection. So I got a lot of emails saying, Dave, can you confirm whether this is an injection or not? And I would send back, no, this is not an injection. And at that point, interest ramped up very dramatically. By the end of that day,
I think a number of, probably the entire collaboration knew we had something really hot.
I'll just add a little bit more. I talked a little bit about this dream of multi-messenger astronomy, where you could see simultaneously on the ground with radio telescopes, with a Fermi satellite, and gravitational waves coming in all at once. An important necessity for that to work is that we be able to identify the signal as soon as possible after it's detected. It was 3 minutes after the waves crossed the Earth that we had a signal that was unambiguous and clear that said, something has happened here that requires attention. For me, it was, again, when I first woke up 3 hours before Dave did, I'd been actually working with a close European colleague in Germany on just this question of whether or not we could perform injections. And we've been pulling our hair out because we knew technically we had a problem that we needed to solve before we could properly do the injections. So he thought only 4 people knew, but I knew also it couldn't be an injection. We didn't know how to do them at that moment. So it took only minutes to realize that something had changed, but it's taken months for me really to integrate it into my vision of things. You work on something for 40 years, dreaming about the day when the detection will come. It takes months for it to finally sink in.
So very quickly, first of all, this gave me an opportunity to walk into the director's office and say, I have good news for once. But I want to say something about the collaboration, because we watched as this information propagated through and our program officers learned about it and all. The way the collaboration handled this is a model of how you do modern big events in science. The rumors were circulating, but they vetted the signal, they wrote the paper, they had it reviewed, they had it published in a premier journal before they had it reviewed in a premier journal before they had the press conference announcing the result. That's the classy way to do science.
Thank you, Mr. Perlmutter. The gentleman from Alabama, Mr. Palmer, is recognized.
Thank you, Mr. Chairman. Dr. Retzi, in 2014, BICEP-2 experiment team announced that they had found evidence of gravitational waves, but the observations were later shown to be the result of galactic dust and were discredited. How confident are you that this or some other type of error is not responsible for the detection of gravitational waves in this case?
Yeah, that's actually an excellent question, and one that we worried very much about ourselves. I think first of all, the thing you can say about it is that we actually had 2 different detectors. We had the one in Louisiana and the one in Hanford. They're independent. They're operated totally independently. They're uncorrelated. They both saw the same signal. It had the same characteristic in signal. The data that we analyzed from that actually showed that the signal was completely consistent. It was found by many different methods. There were a lot of other checks that were done because, as was mentioned before, there are other things, noises that can creep in. So we looked at our detectors and convinced ourselves that there was nothing that was perturbing our detectors. We also did a statistical analysis without going into much detail. We calculate what's the probability that this could actually be false, and how many, if you had to run for how many years, would you see an event that looked real was false. We couldn't actually put a bound on that number. It's more than 1 in 200,000 years. That said, we also looked at other things. Could somebody have maliciously done an injection? We talked about injections. Could somebody have secretly hacked into our computers and done this? We checked every path that we could think of, and even some that we couldn't think of after we thought about it a little bit more, and convinced ourselves that no, that was not possible either. So I think the answer to the question is I think we're very confident. I would say this too, we expect to see more of these signals. So we hope that in the next, the data that we still have sitting, we're analyzing it right now, that we'll see more of them, and having more of them gives you confidence.
Let me give you somewhat of a follow-up on that, and any of you can answer this, and that's the practical application of this, because as my colleague, Mr. Massey from Kentucky, and I were discussing, GPS doesn't work without relativity. Do you see any practical application of this? And I'm not implying that this is not valuable for the sake of science and science. What would any of you see as a practical application? That doesn't mean my time's up.
Yeah. of detecting gravitational waves. It's hard to see anything in the short term. Some people, for example, thought about you might be able to use them for communication because they go through everything. I mean, your bodies are being, my body's being bathed by gravitational waves right now. But it turns out that to generate them, you need big, huge black holes. So it's hard to see that. I think in the short term, and I feel more confident talking about the short term, the things that we'll see that will come out of this research are the technology transfers that come from the work that we do to build these detectors in computing and optics and lasers, servo controls, vacuum systems, things like that. Fundamentally, it's hard to see, but again, for me, this is inspirational because it allows us to see the universe in a way we've never seen before, and for all of us, that's why we got into science. That's why we like to do it.
I really love the GPS mention that you make, because it's certainly the case that when Einstein did general relativity, he had no idea it was going to help me find a Starbucks. and it really is, there are remarkable things like that in the future, but as I said before, I wish I could tell you which one. I think we all do, but they're out there.
I have to credit Mr. Massey with that question. It helps to sit by a physicist from MIT. Engineer, okay. Dr. Shoemaker, not long after the announcement on February 11th, the Indian cabinet granted approval for LIGO India project. Can you give us an idea of the impact of additional observatories coming online?
Yes. The really wonderful thing about the India opportunity is that it's in the far to the south of all of the other existing detectors. We have the Hanford, Washington, and Livingston, Louisiana detectors. There's the Virgo detector from Italy, which is in Pisa. There's Kagra, which is a Japanese detector. But if you look from a big distance from the Earth, they're all pretty much in a line. And the wonderful thing about the India site is that it's to the south of that. And that gives us a bigger tripod that we can use to look in the sky and try to localize the source of a gravitational wave. And it will have a remarkable and unique effect on our ability to pinpoint in the sky.
Thank you, Mr. Chairman. My time has expired.
Thank you, Mr. Palmer. And the gentlewoman from Massachusetts, Ms. Clark, is recognized.
Thank you, Mr. Chairman and Ranking Member Beyer. This is truly just a great hearing, and we are so excited about the results. And as he said, Doctor, it just really, this is inspirational science, and sort of fulfills our cravings as human beings for exploration. But what I find really impressive is that, and this has been touched on by some of my colleagues, it's really a decades of partnership and significant funding. I think $1.1 billion total over many, many years, going from basic research to building LIGO. And what I want to know, because I feel this is such a success story for us to tell about what it means when you can talk to your students and say, you can begin, you can end, and you can remain on this project. What that means, how do you put together a project of this size? How do you keep benchmarks with it? How do you manage something that goes on for many different people over such a long period of time and end with the success that you've had? And I certainly appreciate the classy rollout, but I think that, I'm very interested in how you do that, because I think some of the technology that you ended up using, you couldn't foresee in the beginning. So if you could just speak to that.
Let me try and start, and I know David Shoemaker will also have some I think, good answers or good comments about that. First of all, when you get the project started, I mean, the idea of interferometry, goes back to actually the 70s. Ray Weiss and even some guys in Russia thought about it. And so the question is what you then have to do to make this work. And so you write down a list of things that you need to study and investigate. You start investigating them using money from the National Science Foundation, what I would call individual investigator grants, and then you get to a point where you realize that it could work, and that there's lots of work to be done, but it's more of an engineering. You take the ideas that you've tested, you've studied, and you have to engineer them, and then you get into the project phase. And I think one of the things that LIGO, well, first of all, LIGO got started, I think it was the first big major project that NSF had done, and it
had a rocky start to it because, well, you know, it was so big. It was a factor of 100 bigger than anything else had ever done. We'd done prototypes 40 meter that we didn't think of everything. And so there were some management changes that had to take place, but eventually we got a robust organizational structure in place that understands project management, the fact that you have budgets, accounts, and things like that. You have to track them. You have to make sure you're given a finite amount of money. You have to make sure that you build everything you need to build with that finite amount of money. You have to understand how everything fits together, system engineering. So there were a lot of things that we learned and then borrowed to make LIGO work. And I think both initial LIGO and in particular advanced LIGO was quite successful because we take these things that we learn from project management and we apply them to it. So it's actually a testament to not only the scientists, but a lot of business people. We had a lot of accountants and things like that working on doing this. So there's lots to be proud of here.
And was that a different model, sort of having lots of accountants, or was that just continuation of work you'd done before?
Well,
maybe
no.
on
It was a
different
complete. To do big science, you need to have an infrastructure that not only includes the scientists and the engineers and the students. We had a lot of students involved, but you need to have, you know, people that know how to track projects. You need to have people that know how to, you know, track budgets and things like that. So that was something that we figured out once we had to go into the big science model of it, and we put together a structure that ended up being successful.
Let me say that the project model has been very successful in this case due to the very good management it had. But the human side of this is that, like you were saying, there are graduate students whose career in this is in research is 4 or 5 years, not 20.
Right.
But they are still interested. They were then, I was one of those graduate students in the beginning that I knew I wasn't going to be discovering gravitational waves in my PhD thesis. I did a thesis on something that was going to help the construction of this project, the sensitivity of this detector, and that was exciting enough. It's inspiring people to be part of something bigger. And that is what inspires our undergraduate and graduate students to work for a few years, even though some of them have been part of the detection now, but many are proud of having been part of this in the past, and we are attracting many more.
Wonderful.
May I briefly
Yes,
comment?
we do have a time factor involved
Okay.
here, but
I-
please
I-
go on and respond.
Let me just very briefly go from the inspiration to some of the practicalities of doing this. At the foundation, we have these remarkable program officers. The collaboration that we build is through what's called a cooperative agreement. And one of the striking things I've learned that I've been at the foundation is how complicated project management is. And the program officers working with the people in the project, it's really a hand-in-glove relationship. And there's an enormous structure if you're going to spend $400 million of the taxpayers' money, and we're careful about it, and it involves these close collaborations.
Okay. Thank you, Ms. Clark. The
Thank you.
gentlewoman from Virginia, Ms. Comstock.
Thank you, Mr. Chairman, and I'd like to thank our witnesses so much. It's so exciting to see your enthusiasm, and I'm thrilled that we had one of our local high schools here today. I think we still have some of the students here from Oakton and high school and Fairfax, and we appreciate them being here. And I wanted to ask you, even though we don't have that time travel thing that we could do, if for each of you, if you could go back to being in high school and you were looking at this field and you were looking at how someone might get engaged and involved in this exciting opportunity and career that you all have had an opportunity to do, what would you tell them to do today and going forward in their educational experiences, their volunteer experiences, where they can get internship opportunities, and any websites or other resources that you might provide for the committee that we could share with them, or that you might direct them to here today, if you could speak to that.
Let me just start by saying briefly, This field didn't exist when I was in high school. But I think what I found was really crucial was to find something I was passionate about and just throw myself into it. That was really the key for me in being able to focus enough on a topic. You know, I was a young and wild one at one point, and it took finding something and also finding someone. It wasn't actually when I was in high school, but when I was at the university that I found Ray Weiss, who remained my mentor for all of my career, someone who was inspiring to me, somebody who was a role model, who looked to me like they understood what was important and what we were trying to do, and was also good with a soldering iron. And I think those kinds of things, you find somebody that really turns you on, it gives you the focus to actually follow through with things that look really tough when you start out. Thank you.
Let me say that when I was a high school student, I began liking science and physics because I liked asking questions. So that's what you need to do the most. Ask questions. Don't shy away from questions. There are no dumb questions. About material, we do have in our website, in LIGO.org, a lot of material. And we also have people, emails of people who you can contact to ask any questions. And we are receiving lots and lots of questions, and we answer them all. And we also have some material for teachers to use in their science classes. And there are also programs organized by the American Physical Society for high school, like Adopt a Physicist. So you can ask teachers to contact LIGO people, collaboration people, to act as a consultant and answer
So is there like a
questions.
package we can give to our high schools?
There's a
you all
K-12
have?
package
Great,
for
okay.
students that we have developed. Yes, and there are a lot more material there for teachers and students.
Right, thank you.
Just to follow up a little bit, one of the things that I think is very important, more when you get to the college level, but it can happen at a high school level, is to go up to a professor, all right, and ask them, is there interesting research that you're doing that I can get involved with? So all of us got started actually doing research as college students. You know, we hadn't even decided what we wanted to do yet. And even in high school, so at Caltech, for example, we have, just in LIGO alone, we take in 3 or 4 high school students every year, all right, and we give them a pretty well-defined project, and we mentor them to make sure that they get through it. They get exposed to seminars and things like that. And I suspect that a lot of universities, especially in the Washington, D.C. area, there are a huge number of universities. I would imagine that those kinds of things exist here too. And if they don't, they're not that hard to set up. So.
I want to associate myself with the comment about passion. I think being passionate about science is something that's driven us all. As far as this, and this research comment is an important comment, and the foundation supports research experiences for undergraduates to just provide that kind of an opportunity. There are programs in our EHR that reach down into into K through 12. I want to make one brief comment, though, about how your question relates to how we function as a nation. I am a child of Sputnik. That event and the focus on science directed many, many people for more than a generation into science, and the nation made a huge commitment to our being the global leader in science. Those kind of moments are the things that will invite these folks to come in.
Thank you. I appreciate that passion, and for the students, these are your role models that you're looking for in the science field. If they look and sound like this, grab them. Thanks.
Thank you, Ms. Comstock. The gentlewoman from Oregon, Ms. Bonamici, is recognized.
Thank you very much, Mr. Chairman. What an exciting topic, and thank you so much for holding this hearing today so we can learn more about this very exciting research. And I wanted to align myself with the comments of Mr. Tonko and others about the value of taking risks and the value of this sort of persistence and perseverance over the years and sometimes decades. I want to take just a moment to acknowledge my alma mater, the University of Oregon, for their efforts in this discovery. The university was one of the founding groups of the LIGO Scientific Collaboration. And I know that the university scientist, Dr. Robert Schofield, participated in testing the detectors at the site in Livingston, Louisiana on the day that the gravitational wave was recorded, and almost simultaneously, the LIGO's partner site in Hanford, Washington, where a University of Oregon graduate students were stationed, registered the wave. University of Oregon is responsible in part for the environmental monitoring and really investigating that the wave was in fact a gravitational wave. When anything happens in the Northwest, we think it's an earthquake, right? So they in fact confirmed that this was a gravitational wave, and I know Professor Fry as well, Raymond Fry, who leads the university's physics department, and their team on the LIGO project that includes 5 PhD students, a postdoc, and 3 faculty members. So I'm proud of the University of Oregon. I know that their report really helped the scientists with their confirmation. One of the problems with being one of the last members to ask a question is that a lot of the topics have already been touched on. I was actually in an education hearing with the acting education secretary, so I wanted to ask if you could follow up a little bit. I know the question was asked about how we can get materials to teachers in classrooms, but I also was wondering if a researcher who's unaffiliated with the LIGO collaboration has access to the data.
Yes, we have, in LIGO.org, you can find the actual data, 1 hour of data before and after the detection, and people have already downloaded and are analyzing it. We are we have made the data from initial LIGO runs. They are also available, and people have been looking at that. And we will make the 4 months of data that we have taken available to the public in the future. So we are very committed to open access and the public access to the data.
Terrific. And I really appreciate all the comments that I've heard all of you make about the importance of engaging, especially students, and the internship opportunities, and how do we help students follow their passion. I know Mr. Loudermilk was talking about the app challenge. My office did that as well. I had Adam Barton from Sunset High School win the app challenge. He also happens to be a very talented pianist, which is confirming my theory that integrating the arts into STEM results in more creative, innovative people. Do any of you have any sort of new approaches to bringing, first-generation students, for example, and students from underrepresented groups into the STEM fields?
Yes, we are very committed into increasing the diversity, not just in our collaboration, but in general in the scientific community. We have been working very closely with the National Society of Hispanic Physicists and Black Physicists for including, for affiliating students and teachers from colleges with large underrepresented minorities. We work with several of those universities, like Southern University, University of Fullerton, University of Texas, Rio Grande Valley.
Thank you for that work. It's important to get them interested and also to retain them by having positions and having good working environments. And then finally, I know it's been touched on this morning, but could you expand a little bit on the importance of international collaboration? I know that there was a lot going into this, but we also talk about this when we talk about space research. And, we have jurisdiction over NASA, for example. Can you talk about the importance of the international collaboration with LIGO in this discovery?
Yes, we are very proud of having had a very international effort on this. It's been led by the U.S. The U.S. has been a leader in this effort, both within the the LIGO scientific collaboration, which is an international collaboration. We have been leading this in the U.S., but also leading, uniting all the other collaborations, getting agreements with all the other collaborations so that we don't compete with each other, but we collaborate for better science. We collaborate in forming a network. And that has been very important and very efficient too, because we have recruited many students and scientists from other countries to help us here in the U.S., for example.
That's a great model for collaboration. And my time has expired. I yield back. Thank you again, Mr. Chairman.
Thank you, Ms. Bonamici. That was very deftly done to include the University of Oregon to the extent that you did. Totally understandable. Thank you all for being here today. This was really a special and even unusual hearing, just because there was so much to learn and so much excitement about a new discovery. It's also nice, I think, from our point of view, just to see how much mutual support there is among you all, how much collaboration, even camaraderie, perhaps. So appreciate that. We had a full house when we began today. They've trickled out over time, but it was nice to start off with every seat in the room occupied, and a tribute to what you all have done. So thank you all very much.
Thank you all for holding this hearing.
Thank you, Mr. Chairman.
Thank you.